In this lecture, we would like to apply the Caratadori and Hankel-Mogorov extension theorems in constructing the Lebesgue measure on the Euclidean space Rn. So to start, let us recall some facts that we have established in the previous lectures. So first, we have the summering of cells in the set of real numbers, and that would be script I. So recall that this script I is the collection of all half open, half closed intervals with endpoints in the set of real numbers, and the left endpoint is less or equal to the right endpoint. So for instance, if A is equal to B, then you get the empty cells. And from this, we have the elementary content in R. So we denoted that by kappa. So kappa is defined on all cells. And this kappa is basically equal to, so the content or elementary content of the cell is the difference between the endpoints. So this is clear that this is non-negative because A is lesser than or equal to B. And therefore, the triple, so you have your set R, collection or the semi-ring of cells, and the elementary content. We shall call this as the elementary content space on R. So from this, we now construct the semi-ring of cells in R. So I sub n, this is what? The Cartesian product of I with itself n times. So you just take the Cartesian product of cells in R. That would be your cells in Rn. And we have a theorem that this is indeed a cell, or indeed a semi-ring, because the product of semi-rings is again a semi-ring. That is Hans' theorem last time. And if you have a content on a semi-ring, then the product of those contents are also contents in the product space. So in that way, we can also create the elementary content on Rn as follows. So this would be kappa n. This is now defined on the semi-ring of cells in Rn. So again, kappa n here would be the product of kappa n times. Well, more concretely, if you have, let's say, a cell AB where A has components, let's say, A1 up to AN, and B has components B1 to Bn, and let's say A1 is less or equal to B1, and so on up to AN less or equal to Bn. then this is the product of the contents of the corresponding one-dimensional cells. So this would be B1 minus A1. You take the product until Bn minus An. And that will be your elementary content on Rn. And analogous to the one-dimensional case, so you have Rn, the cells in Rn, and the elementary content kappa n. We will call this the elementary content space in Rn. So take note that if n is equal to 1, then we just end up with the previous elementary content space. Now, we want to consider the ring generated by the cells. And this will be denoted by Fn. Okay. So this is the ring generated by the cells. The F here comes from the fact that we shall call pairwise disjoint union of cells as figures. So ring of elementary figures in Rn. For instance, in the two-dimensional case, this will be your typical cell, half open, half closed. Okay, so open on the left and at the bottom, and then close at the top and on the right. So if you add, let's say, another cell here, take the union, then the union would be, so subtracting this part. So this would be an example of a figure in R2. So basically a combination of, how do you call this, of cells in R2, in this example. Okay, so you can, of course, extend this by adding more cells. Now, according to Hans' theorem, we could generate the premeasure, okay, which we simply denote by kappa n, okay, on the ring of figures. And this is also a content. So what we did here is that, okay, you have a content on the semi-ring of cells. We can extend that into a content on the figures, where the figures in Rn are basically the sets in the ring generated by the cells. Okay. Here, to apply the Karategori and Hankel-Mogorov extension theorems, we want to establish that kappa n is not only a content, but also a, let's say, a premeasure. In fact, it is also sigma finite. Okay, since according to this statement here, We already know that it is a content. So it remains to establish that kappa n is additive. Proof. Okay. We need to show that kappa n is additive, or is sigma additive to be precise. So let us take cells C sub k from 1 to n. Okay, and this is, let's say, pairwise disjoint. Well, it is enough to prove that kappa n is sigma additive on In. Because in that case, in fact, we could go back to the previous discussion here. So we know that this is a content. In fact, it is a premeasure. Okay, if we can show sigma additivity. Now, if your elementary content is also a premeasure on the ring or the semi-ring of cells, then again, applying Han's theorem, if you have a premeasure on the semi-ring, you will also get a premeasure on the semi-ring. So that would be the one that we only need to prove. We need to prove additivity or sigma additivity of kappa n on the cells. So that's why we only took here a collection of pairwise disjoint cells in In and not on the elementary figures, because this will simplify the proof, of course. And let us denote by C the union of these cells, C sub n, and let us assume that this is also a cell. Okay, being a cell, this means that C can be written as alpha beta for some alpha and beta in Rn, and without loss of generality, we suppose that alpha is strictly less than beta. In other words, the corresponding components of alpha is strictly less than the components of beta. Otherwise, this would be an empty set if at least one of the components are the same. Okay. And a cell, the empty set is considered as a cell. So now, having said this, let us also write the cell C sub k as what? A sub k, B sub k. Okay, and let us use a superscript to this distinguish between components. So for some A sub k, B sub k in Rn, and suppose that with the same, of course, idea, we suppose that the left endpoint is strictly less than the right endpoint, because otherwise CK would be empty. So to prove additivity, let's start with what? With the sum of the elementary contents of the cells, so C sub k, k from 1 to infinity. Of course, this series is equal to the limit of the partial sums k from 1 to n, as capital N goes to infinity. Okay, here the trick is to apply additivity of kappa n. Okay, but not on the cells, but on the set of figures. So kappa n from f n to this set is a content. Hence, it is additive. And take note that this is what? In the ring of figures, this is a cell, hence also a figure. So we apply the additivity of kappa n with respect to the figures. And if you see here, the partial union is smaller than. So it's a subset of the whole union, C, okay? So each of these terms here is less or equal to kappa n of C, because C is larger than the partial union. Hence, the limit would be bounded by this kappa n of C. Take note that C is the union. And let us recall that here. So C is the union of the C subcase. So that's one inequality in additivity, sigma additivity. To prove the reverse inequality, what we do is the following. So let us illustrate the case for n equals 2. So I have here a cell which is the cell, let's say C. I will take, let's say, a smaller cell. So let us reverse the figure. So let's start with a larger cell, and that is C. And let us take a smaller cell. Okay, so this is recall that C here would be the cell alpha beta. And the smaller cell will be this one in blue. So let us move this to avoid confusion. And this C, let's say C delta, to be alpha plus delta 1, the vector 1, beta. So here the vector 1 consists of the components, or the vector having all components 1, 1. So here we are illustrating the idea of the proof for the case n equals 2. Okay. So let us look at the coordinates. So let's say the coordinates here is alpha 1, beta 1, and here alpha 2, beta 2. So here, this would be the distance of this would be delta, and then the distance with this would be delta. So this point here is the projection of this point, would be alpha 1 plus delta. And similarly, the projection of this is alpha 2 plus delta. So we take a smaller cell relative to the cell C. This is by adding 1 to each of the components of the original cell C. And in that case, you will get a smaller cell. And that would be C delta. So let us write down that in general. So let C delta to be the cell alpha plus delta 1, beta. Delta here is small enough. Small enough in such a way that alpha 1 plus delta will be between alpha 1 and beta 1. And that is possible because here alpha 1 is less than beta 1 by our assumption. And what is that assumption? This one here. So the closure would be the closed cell. And by the way, beta here is also, I should say 1. It's the vector consisting of all ones in Rn. Okay. So that's the closure. And likewise, take note of the closure. So if you take the closure, these parts here will be included in the closure. And that will be still a subset of C. Okay, so let us be careful on the set. So that would be C. This is what? A subset of the C sub k's. Since the C sub k well, this is precisely, in fact, equal to C sub the union. This, the union of the C sub k is equal to C. And let us make the C sub case, in this case, larger. So k from 1 to infinity of, let's say, the components or the coordinates or the endpoints of C sub k is AK, B sub k, but I want to make this larger. Let us denote this by E sub k. Where E epsilon sub k is what? Epsilon times B sub k minus B sub k. Aha, this should be a vector. So let us change the notation here. So this is a vector having the following components. So this should be epsilon times B1 minus A1, B2 minus A2, up to Bn minus An. Okay, so that's the vector that we are taking into account. So here, the idea is similar to what we have. So let's say, let us illustrate this in the two-dimensional case. So we begin with C sub k. You add an epsilon on the right, and then you add epsilon above. This part here will be your cell, let's say AK, BK plus epsilon K. So let us make this as a superscript. So epsilon K. Now what is epsilon? Of course, epsilon is positive. So we add an epsilon unit to the right. Okay. Well, to be precise, this is epsilon what? B1 minus A1. And this is epsilon B2 minus A2. So I messed up with the superscript. So this should be a subscript for components. So this must be what? B1K minus A1K. So therefore, this should be B2K minus A2K. And let us fix that here. This should be A1, or I should say B1K minus A1K until BNK minus ANK. Okay, so that's our vector. And we would like to make this open as well. So this figure here, the boundary should not be included. So let us fix that one. Okay, so that would be our open cell. That would contain a C sub k. So here, so if you look at this one, we have an open covering, okay, of the set C delta closure. You know that this is compact since it is closed and bounded. So according to the Honeyboral Theorem, this is compact. Therefore, we can find a finite set of indices, let's say K1 up to Kr, such that our countable covering can be reduced to a finite covering. So here we have A, let's say K, J, then B, Kj, plus epsilon Kj. Okay. Take note that the closure contains the set, because the closure is the smallest closed set containing the set for the cell C delta. So thus, we could now, well, in this case, let us include, okay, the endpoints. And let us denote this by dkj. This dkj now is a cell because it is now closed on the left-hand side, right-hand side. And if you take the content, elementary content of dkj by a simple calculation, okay, you could verify that this is 1 plus epsilon n times b sub k1, or I should say the content of c sub kj. So this is by applying, of course, taking by using the definition of kappa n, you have 1 plus epsilon here because you will get an extra factor on epsilon here. So each component will give you an extra epsilon on the width. So therefore, with respect to the n-dimensional content, you will have an extra factor 1 plus epsilon of the original cell CKJ. Okay. By the monotonicity of a pre-measure of a content, because so far we know that kappa n is a content. So kappa c delta, kappa n c delta would be less or equal to, okay, based on this covering here, the kappa n dkj, and take note that this one is less or equal to 1 plus epsilon raised to n kappa ckj, j from 1 to r. Okay, so this is just a partial sum. What if we take the whole sum? Then we still have the same estimate. So we can replace this by 1 to infinity. Okay. Let us look at the left-hand side. Kappa n c delta. So the way we defined this cell c delta, this is alpha plus beta 1, the vector 1. I should say delta times the vector 1, beta. This tends to kappa n of the cell C as delta goes to 0, since it's alpha plus delta 1 increases with C. Okay. Well, you can take a sequence if you like, but that would be the case. So we can now pass delta to 0 and then epsilon to 0. So passing delta to 0, we get instead the elementary content of the cell C. Here, if you pass epsilon to 0, the coefficient here would tend to 1. And then we get the sum of the elementary contents of C sub k. And this is the what? The reverse inequality that we would like to establish. So here is one inequality. So the kappa n of the union is greater or equal to the sum of the kappa n's. And we have the reverse inequality. Hence, kappa n is also a pre-measure on the cells In, and by the Han extension theorem, kappa n is also a pre-measure on the elementary figures. We also need to show that it is a sigma finite. Well, that is quite easily shown in the following. Kappa n is sigma finite since you can cover Rn with the following cells, negative n, 1. So this is a vector having components negative n, and you take the positive ones, you take n 1 to infinity, and you get the Euclidean space Rn. I should use a different index. I should use k, let's say k, from 1 to n. Okay, so that's the sigma finiteness of the elementary content. Take note that this kappa here looks k. Okay, so let us make a distinction. So negative k. The measure of this, or I should say, the content of this is equal to. Well, you can calculate. This is finite. Okay, so if I'm not mistaken, this is 2k to the n. Which is obviously finite. Okay, since each interval would produce a 2k length. So that would be what? An n-dimensional prism having side length 2k. So therefore, or in fact, this is an n-dimensional cube or hypercube having a length, side length 2k. So the elementary content would be 2k raised to n. Okay, so we now establish the fact that this Rn, In, kappa n is now sigma finite pre-measure space. Okay. So applying Han's theorem, we can extend this into a sigma finite pre-measure space, but now on the set of figures. And here we still denote the content by kappa n. Or I should say, let us change the notation. Let us change that to lambda n. Okay. And this is also called we shall call this the Lebesgue pre-measure space on elementary figures. Now, let us denote by lambda n star the outer measure induced by our pre-measure, or I should say Lebesgue pre-measure lambda n. And if we apply Caratio-Doris extension, so we have the Euclidean space Rn. You take all measurable sets with respect to the Lebesgue outer measure. So this will be called the Lebesgue outer measure. And then you take the restriction of the Lebesgue outer measure to the Lebesgue measurable sets. This will be called the Lebesgue measure space on Rn. Okay, so that would be this will be your Caratio-Dori extension of your Lebesgue measure, pre-measure, lambda n. And similarly, if you take Rn, and okay, before we proceed, let us look at the sigma algebra. So what is the sigma algebra of the cells? We said that this is the same as the sigma algebra of the ring generated by the cells. And this is the same as the sigma algebra generated by the figures. But as we know from earlier discussions that the sigma algebra generated by the cells is nothing but the Borel sigma algebra. Okay, so here we have the Borel sets in Rn. And you restrict the Lebesgue outer measure to the Borel sets. This will now be the so-called Lebesgue-Borel measure space on Rn. And this is basically your Hahn-Kolmogorov extension of your Lebesgue pre-measure. Okay, so there are two ways that we could extend the Lebesgue pre-measure space on the elementary figures, and that is by the Caratio-Dori extension, and we get the Lebesgue measure space. And the elements of this sigma algebra will be called the Lebesgue measurable sets. And this measure here will be your Lebesgue measure. And the other one is that you could construct the Hahn-Kolmogorov extension of your Lebesgue pre-measure, which is basically obtained by restricting your Lebesgue measure to the Borel sets. Okay. And this measure will be now your Lebesgue-Borel measure. In the succeeding notations, because these measures, the Lebesgue measure and the Lebesgue-Borel measure only differ on the domain. If it will be clear in the context, we will simply denote these two, the Lebesgue measure and the Lebesgue pre-measure, or the Lebesgue-Borel measure, I should say, So with abusive notation, we simply denote this by, again, adapting the notation for our Lebesgue premeasure lambda n. Okay, so this lambda n will either refer to the Lebesgue premeasure, the Lebesgue-Borel measure, or the Lebesgue measure, depending on the set that we are applying to this measure. The context will be applied. In other words, if your set is, let's say, a measurable set, Lebesgue measurable set, then you should use the Lebesgue measure. If your set is a Borel set, then you can use the Lebesgue-Borel measure. Okay. Well, this is well defined because the restriction of the Lebesgue measure to the Borel sets is the Lebesgue-Borel measure. And on the other hand, the restriction of the Lebesgue-Borel measure to the elementary figures or to the cells is nothing but the Lebesgue premeasure. So this abusive notation or simplifying notation does not lead to any contradiction. And that's the construction of the Lebesgue measure space on Rn and the Lebesgue-Borel measure space on Rn. So the Lebesgue-Borel measure space is in fact the one that is utilized in probability theory. Next lecture series, we will ask, okay, what is the difference between Lebesgue measurable sets and Lebesgue-Borel sets? That's it for now, and see you on the next one.